Good morning, everyone. My name is Minji Chan from Gunma University in Japan. Today, we would like to present a design of an Acti inductor and the stability test for passive RLC robot filter. There are 4 parts in my talk. First, we will review the basic background and we focus on the concept of the cell-loop function in a transfer function. And we also discuss some limitation of the conventional stability test. In the second part, we analyze the second order transfer function and the cell-loop function. We emphasize on the stability test for the second order system. In the third part, we show our experimental result and we conclude our work in the fourth part. As you know, the ringing or the overshoot occur in many systems. They occur in both feedback and without feedback system or in both passive and active networks. When a system operates in under damping region, the damp oscillation noise call the system unstable. So we have to do the stability test to improve the overshoots. The objective is this work. We will investigate the behavior of a high order system both in the time and frequency domain. Especially, we will investigate the phase machine of the cell-loop function in case of underdamping region. The theoretical analysis will be verified by the practical measurement. First, we will analyze the typical second order passive RLC robot filter, and then we will replace the passive inductor by active one. We use a general impedance converter to design an active RLC robot filter, and we verify the analysis by the practical measurement. Now let me review the characteristics of a complex function. As you know, when a system, we can model a network using the transfer function, and we can express the transfer function and the cell-loop function of a network in the complex plane domain or in spectrum domain. We use the polar chart or Nyquist chart to express the transfer function in a complex plane, and also now I think all of you already know the body plot. In another way, we can compile the magnitude frequency plot and the angular frequency plot into one diagram, which is called Nicholas diagram. Next, let us define the concept of a cell-loop function in a transfer function. When a linear system is defined by the transfer function, we can model this system by the ratio between the output signal over the input signal, and here we define A of omega is the open loop function, and the denominator part of the transfer function, L of omega, is the cell-loop function. When the denominator of the transfer function equal to 0, this transfer function is very large. It means that this system is unstable. So the convention, the constraint for the oscillation is the S unity gain of the cell-loop function. The phase is equal to minus 180 degrees. In this work, we use the concept of phase machine as the unity gain to investigate the behavior of a network. From the transfer function, we can express the behavior of a an analog network using a signal flow graph. And you can see the characteristic of a negative feedback network is the same as the behavior of a transfer function. To get high stability, fast transient response, and good steady state performance, we have to do the stability test to investigate the behavior of a system. In this work, we propose a method named comparison measurement to derive the shallow function of a network. First, in step 1, we measure the open loop function, and then we measure the transfer function. After that, we derive the shallow function. This method is used to derive the shallow function in Acti networks. Another way we also report the alternating current conservation to to measure the shallow function in practical measurement. The basic idea is that the alternating current is conserved. It means that the incident current is equal to the transmitted current, and now the shallow function is defined by L of omega E equal to minus the incident voltage over the transmitted voltage. In simulation, we can use the voltage short or the current short to define the shallow function. And in this work, we use Busy balloon transformer to measure the shallow function in the implemented circuits. We also report the widened superposition principle to calculate the transfer function in a multi-short system, feedback network, or polyphase filter, and so on. The widened superposition principle states that energy S1 plane is proportional with their input source and the resistance distance. Now let's discuss the conventional middle roof methods. This method is used to measure the loop gain in feedback system, especially in switching DC to DC converter. And it's very difficult for us to measure the shallow function in Busy network or Acti network using the conventional concept. And another way, the replica measurement can be used to define the shallow function, the loop gain in the feedback in Acti network. But if you use this method, we have to compare to identical network. So it is very difficult for us to apply this method in practical measurement. And the conventional superposition to investigate the behavior of a network with many sources, we have to separate each source and take in turn to calculate the behavior of a network. So it takes several times. And the conventional Nyquist stability condition, if we use the polar charge of a loop gain, it's very difficult for us to define the phase machine of a network and the unity gain. And sometimes you can see in some paper that the conventional concept, the analysis and the measurement of the loop gain are not unique. So let me show a simple typical second order system. In this work, we show a second order parallel RLC low-pass filter. After applying the superposition principle, we can define the transfer function and the shallow function easily And we can see that the function are second order complex function. And the operating region can be defined based on the chosen basic component, resistor, inductor, and capacitor. Now let us show the summarize behavior of a second order transfer function. You can see at the cutoff angular frequency, the magnitude of the transfer function in case of critical damping is to A0 over A1. And in case of underdamping region, the magnitude is greater than A2 A0 over A1. And now let us show the numerical example of a second order transfer function. In case of underdamping region, we can see that the magnitude is greater than 1. It means that the gain of this transfer function will amplify the harmonics, the high order harmonics of the input signal around the cutoff frequency. Now let us show the body plots of the transfer function in 3 cases: underdamping, critical damping, and overdamping. And you can see that in case of underdamping, the magnitude of the transfer function is greater than 0 dB. It means that the harmonic at around the cutoff frequency will be amplified. And the conventional language can express the behavior of a transfer function. Next, let us show the summarized behavior of the second order Sherlock function. And you can see that at the unity gain of the Sherlock function, the phase margin is 76.3 degrees. In case of overdamping, the phase margin is greater than 76.3 degrees. In this case, the rising time is very slow. Now let us show the body plots of the Sherlock function. In case of critical damping at the unity gain of the phase margin, we can see the phase is 103.7. It means that the phase margin in the critical damping is 76.3 degrees. The simulation result is the same as the theoretical analysis. And you can see in time domain, the overshoot occurs. It's very high. Now let us review the behavior of an ideal op-amp. When we design an Acti network, in a commonly way, we use Acti device, especially op-amp. And in this research, we saw the behavior of an ideal op-amp. We investigate the Sherlock function and the open loop function of an ideal op-amp. In this work, we use 10 MHz gain bandwidth and the DC gain of the ideal op-amp is 100,000. And now let us show the behavior of the open loop function. On the body plots of the open loop function, we can see that at the bandwidth frequency, the gain is 100 dB, and we can express the open loop on using language chart as shown on the right. Next, let us show the behavior of the Sherlock function in an ideal op-amp. We can define the Sherlock function based on the comparison measurement as we report. And we can see that at the unity gain of the Sherlock function, the phase margin is 90 degrees. It means that this op-amp is absolutely stable, and we combine the plots into one diagram, which is called Nicholas diagram. And we can see that from low frequency to high frequency, the phase machine is equal to 90 degrees. Next, let us show the design principle of an Acti inductor. We replace the passive inductor by an Acti one. In this, we use the principle of general impedance converter. After applying the superposition principle at the node V3, we can approximate the value of the impedance of an Acti inductor like this. And now let me show the simulation result of the passive stereo RLC robust filter and the Acti one. We can see that they are the same characteristics. And now let us show the implementation of a passive second order stereo RLC robust filter. We can see that the ringing occurs at both the input and the output port. And the body plots of the transfer function, we can see that in case of underdamping region, the magnitude is approximately 3 dB, and the overshoot is very high in time domain. The measurement results show that the phase machine is 55 degrees in case of underdamping region. So this system is unstable. Next, let us show the measurement result in case of Acti RLC robust filter. The overshoot occurs at the output port, and in this case, the magnitude of the transfer function in case of underdamping region is about 7 dB, and you can see the overshoot occur in time domain. And the phase machine in this case is 65 degrees. Now let's conclude our work. In this presentation, we review some characteristics of complex function and the stability test. We also propose some methods to derive the transfer function and measure the self function. The theoretical analysis is verified by the practical measurement. If the phase machine is smaller than 76.3 degrees, this system is unstable, so we have to improve the overshoot. In future work, we will investigate the behavior of high order polyphase filter and complex filter. That's all for my talk. Thank you for your kind attention.